See how this goes. Good morning, everybody. We're going to be talking about the work energy theorem, unit 3 from the College Board for AP Physics C. They don't ask too much in this. A couple things that you'd want to be aware of is that work and energy share a symbiotic relationship. Energy is the ability to do work. The way you change the energy of a system is you do work. That cyclical process. And then some of the things initially that they want you to be aware of. How would you calculate work? You need to be aware that it's a scalar. That comes into the fact that it's kind of like scalar is interesting, but kinetic energy can never be negative. Something to think about. You can add energy to a system. You can take energy out of a system, and you can do no change to the energy of a system. And then we need to be able to solve some kinetic energy. In addition, we have a few more things: potential energy, and then using the ability of conserving energy and power. So with work, we always think of work as force times distance, but you want to make sure that you're aware that they are parallel to one another. So you might be looking at it like F11 or F parallel to the distance or the displacement that the work is done. The force is applied. An example of that is taking a block and exerting a force on the block to the right as it moves to the right, some distance d or x. If I apply a force of constant force, we know that force would make the object accelerate, and as a result of that object accelerating, its kinetic energy would change. So we could say that the amount of work done is equal to the change in energy as long as they're applied parallel to one another. Now, we can do a few things here. We could say that obviously this surface would have to be frictionless in order for us to use that idea of force times distance to get that change in energy. So we think about that. You would just do force times distance, and that equals the work, which equals delta KE. Solve for the change of velocity. All those kind of things could work. You could also solve for it a different way and just identify that F equals ma, which is still a good and true statement. So that's the first introductory idea. And thinking about that, if it starts with no kinetic energy here, it's at rest, and here it's going fast, we could figure out how fast it's going with this information. We're using K as kinetic energy. How could the work be negative? How could the work be zero? You might be asking yourself, or the College Board may ask you, how could you have that scenario? So I have an object, and I exert a force up, and it moves up some distance. Notice that the direction that it moved was up, and the force that was applied was up. That tells us that the amount of work is positive. When they're in the same direction, the amount of work is positive when they're parallel to each other and in the same direction. How could they be negative? Well, if I had an object up in the air and I lowered it, just doing something like it's up in the air and I lower it, I hold it in my hand, I lift it up, that's positive work. But when I set it down, that would be negative work, and that's because I am exerting a force in the upward direction as it moves a distance downward, noting that the force is applied up while the distance is applied down. The angle between those two is 180 degrees. They're parallel to one another, but they're anti-parallel. A fun word to say that they're 180 degrees apart. Being that they're 180 degrees apart, we could say the cosine of 180 degrees, if you're in degree mode, ultimately ends up to be -1. So you can also think that work is equal to force times distance times cosine theta. And when they're 0 degrees apart, our work is positive. When they're 180 degrees apart, the work is negative. And then when they're perpendicular to each other, or there is no change in energy, the work is 0. An example of that is the traditional waiter question, where the waiter has a tray, waiter lifts up the tray, then carries the tray across the room, then sets down the tray. The waiter's hand is located here, so that's the force applied. To lift it up, we have positive work here is 90 degrees. It is 0 work. And finally, when you set it down, it's negative work. So keep that in mind. FD cosine theta, or F parallel to D. And when they're opposite directions, completely opposite directions, you have that case. Occasionally you get the extra question, you know, the pushing an object or pulling an object. So you have a block that is located on the ground and you exert a force in this direction. The force applied upward is less than the weight of the object. Therefore, the object only translates to the right. It moves a distance d. So when you're solving this problem, you need to make sure you're taking into account only the force parallel to the distance it moved. And as that happens, we want to do F cosine theta. So force cosine theta times the distance d tells us the work done by that. As long as it's frictionless, we don't have ourselves a problem. And we can just say that's equal to the change in kinetic energy. So when we think about kinetic energy, which I've referenced a few times, we want to be aware that kinetic energy depends on how fast an object is going, but it would also depend on the amount of mass an object has. And the College Board does provide to you the kinetic energy of an object is 1/2 mv squared. We derived the kinematic for that last week. Right? We used kinetic energy with potential energy to derive the kinematic that said this. So as long as you apply a force over a distance, we could say for that case that we just did FD cosine theta. And as long as that is the only force acting on the system, we could say that is equal to the change in kinetic energy. So we would say VF squared minus VI squared. Given that the 1/2 and the m, the 1/2 is constant and the m is just the mass of the object. The only thing that would be changing is this. Something to keep in mind is that you need to fill out the calculation because it's 1/2 mv squared. So make sure you do the squared parts. Otherwise, you get yourself into a trap. But you don't have any multiple choice questions on this year's AP Physics C exam. So calculate work. It's a scalar. It can be positive, negative, or 0, and it does this change in kinetic energy. You might be looking right here. That's a fancy way of saying force times distance. However, occasionally, you might have yourself a situation where you have a non-constant force exerted over a distance, and the way you would find out the amount of work is the area underneath that curve. And using calculus principles, you can just integrate over that whatever values you want on your horizontal axis. So you could say from A to B, and then have your force as a function of distance, and that looks like some slope, and then where m is the slope of the object, and if you take the area underneath this curve, you would find the work done on it. So keep that in mind as you move forward as an extension of that idea of force times distance. You could also integrate. All right. Now we got a bunch of stuff on this one. We got to talk about what a conservative force is versus a dissipative force. Sometimes it's referred to as a non-conservative force. What the heck is potential energy? How do we graph all that stuff? Some potential energy concepts with Hooke's law, including elastic, and then some gravitational potential energy. And then some of this stuff, because of the level of detail that I talk about this in our initial conversation, I'll be discussing farther and more deeply in our conversations on Wednesday, and also in office hours if you have some questions about all of that. So what the heck is a conservative force? I have an object that is located here on the ground. and my ultimate goal is to get it on top of this table some HI. So I have object M, and I want to get it on top of this table. Now, we think of the most direct path as just being pick it up and set it down on the table. So we have an initial location and we have a final location of that box. What a conservative force is it doesn't matter the path that you take. All that matters is where you begin and where you end. So the first conservative force that you would want to be aware of is the force of gravity. It's down always. And it doesn't matter if I lift this object up like this and I move it all around through empty space, so long as there's no external forces on it and I set it down right there. All I need to be aware of is where I started and where I ended to describe that as a conservative force. That's all the work done by that conservative force, equivalent to, in this case, the change in potential energy, mgh. So that's the first idea of what you want to be about with conservative forces is where does it start and where does it end? And if that's all you need to know, then it's conservative. However, a dissipative force, and the most common dissipative force that you have is friction. So I have an object that is sliding to the right with some velocity initial v. And it's sliding to the right. And we would observe, since it's sliding to the right, the only force that would be acting on it, in this case, would be the force of friction. So as I slide it to the right, we see that the force of friction is to the left. Alternatively, the block is now located on the right, and it is now sliding to the left. We would identify now that the force of friction is to the right, noting that the force of friction has changed the direction in which it's exerting a force. So it doesn't just matter on where it starts and where it ends. It matters on a few other things, like which way is it going? So because the force of friction can change direction based on the scenario, we have to say that it is a non-conservative force or dissipative force, meaning it removes energy from our system. In this case, it removes kinetic energy and turns it into a non-mechanical form of energy, heat. All right. Let's see, what do we want to talk about here? So that's that potential energy, stored energy, your forms of stored energy, or what we refer to in my class as UG. And we talk about US. So we talk about gravitational. And we talk about elastic. And what you want to be aware of here is just MGH. This is all stuff that you're aware of. But if I want to change it, we would be aware that we would want to change the height at which the object is located. In addition to that, we would say that the elastic potential energy is 1/2 kx squared. So long as it's an ideal spring, we have to talk about what that means if it's a non-ideal spring. And we're going to focus a little bit more on elastic potential energy. We do a lab with that. We also see it again in simple harmonic motion, which is something we discussed. Let's see how this goes. When I think of an idealized spring, I just think of force versus stretch. When you do that, you get Hooke's law, and you have the force versus the stretch of the object. As a result, we found this nice value, and we found that the force is equal to kx. What we observed was we measured the force that we applied, not the force exerted by the spring. So the spring exerts a force, restoring it to its equilibrium state. So it's always in the opposite direction that it is stretched. And it's attempting to get it back to equilibrium. We graph it this way to see the relationship more effectively. But this is the force exerted by the spring, not the force exerted by us or weight. So then we can use that other concept that says, well, if I want to to figure out the work done, I would take the area underneath this curve, and the area underneath this curve is this function right here. So when I integrate that function, k is a constant. So we got us. When I integrate here, I would say that we have 1/2 k x, change in x squared. Or actually, I want to write that differently. One half k xf squared minus xi squared. And that would be the integral of this. You wouldn't really think about needing to do the integral of this because you see it as a triangle and you just do 1/2 base times height. But you could always define the force here as kx, and you could find algebraically the very similar statement that you get here. Why is it important to be aware of this as being an integral to solve this problem from the beginning and the endpoints that you're concerned about, the final and the initial positions? Is if it's not a linear function, it's a non-idealized spring. And then we just want to say it's the integral of the force as a function of position dx. Because if it's a function that looks like this, where a spring does weird things in the middle, you would just integrate whatever that function is over the two locations that you were concerned about. So that's one thing to keep in mind. You might be asking, what's going on with these negative signs in these statements? Well, the negative sign is representative of the change in energy, where this negative sign cancels out this negative sign that was the force exerted by the spring. So you see this negative that is added to remove the negative of the force exerted by the spring. We find the same situation with the potential energy statement written out for distant objects from the Earth. If you took the change in energy of a rocket, we would say that the force exerted by gravity was in a downward direction, but we knew that it gained height. So then when we find the change in potential energy, we would want to negative the force of gravity on that object in a very similar statement that you have here. We have to undo this negative to talk about its change in energy. So that's something to keep in mind, where this is just force times distance, if you will, where the distance is whatever you are, however far you got away from the Earth, and big G mm over r squared is our statement for force, and you multiply that by a distance, and you see algebraically that we lose one of the distances in the denominator. So this is just a rough idea of what that is. You would want to do the whole statement to figure out the actual value. I'll post some questions so you can take a look at how that might look on Google Classroom. But that takes care of that. Alternatively, you can go forwards and backwards on these two ideas. If you take the integral of this statement, you would know that the inverse, the opposite of an integral would be the derivative. So you could find the force specifically by taking the derivative of a energy position. Okay. This one's relatively straightforward. We're going to be done a little early. My apologies. Conservation of energy. When is mechanical energy conserved? We got to be able to relate all these forms of energy. We got to be able to relate them to T or X and talk about them on a graph. We have to be able to solve for unknowns. And when I talk about unknowns, it'd be positions, velocities, stretches, compressions. All of this could be a value that you could solve for given enough information that you know. How could you do this if it was a non-constant force? Probably calculus, and then solve for heights, angles, and for vertical circles and or pendulum. So that's where we get our L minus L cosine theta statement right there. So that's that NC right here is for a non-conservative force. That's what it has to be to make that statement true. So when is it conserved? Where mechanical energy is conserved as long as there's no external forces acting on the system, or it all maintains mechanical states of energy. You can think about friction removing energy from the system, but we can add that as a form of non-conservative work into our statement. But our traditional question would be a roller coaster. I just talked about this with AP Physics 2 class for fluids, where we have a roller coaster down here located at the end. You have K, we have a position H located here, and you get on your roller coaster. Oops. You get on your roller coaster. I don't know why sometimes I erase with the eraser and sometimes I erase with my finger. Anyway, so we have a mass on that roller coaster. It is going to slide down here. Questions that they could ask along the way is, where is it going the fastest? How fast is it going there? What else could they ask? How much does it compress the spring? If this much energy is lost, how much higher does it, where does it get to on the way up? If there's friction here, how much energy does it turn to heat during that location? So the first thing that you'd want to do is just figure out points that you're interested in. Points of interest for me would be A, probably here B, and then here location C. And then using the statement of just general conservation of saying that the energy at every location is equivalent to the energy at any other location, we just need to identify the forms of forms of energy there. So this statement is very common. Problem-solving technique. Conservation of energy is a great way to start any physics problem because it's conserved. I would say it's number 2 in terms of most effective techniques. So I would say the University of Georgia is equal to the kinetic energy at location B is equal to the potential energy in the spring at location C. Noting that I would say that it has no height here, so it's lost all of its height. So its change in potential energy its change in gravitational potential energy has caused it to have the kinetic energy here. And then the kinetic energy that it strikes the spring will tell me how far it will compress the spring. As a result, we would set up our statement. After identifying variables, we would be able to say mgh equals 1/2 mv squared equals 1/2 kx squared. So we could do a couple things here. Note that you do need to be aware of the mass of this object because the spring does not have a mass component. So we want to keep in mind that we can't just reduce the mass away from all of this. But given that we know the height and given that we know the k, we do possess the ability to solve for, we also know the m. I listed it as m. We have the ability to solve for any location that we want. So depending on which location that you'd want, if I were to ask what is the compression of the spring, we would want to be aware of where does it start and where does it end. And I would look at this statement right here and I would say, if I want to, what do I know the most about? Well, it's asking me how much it compresses, and I know the most about location A, the way the question presented it to me. So I would look at just A and C. I should have said the Trojans. I don't know. I could have, that's the other one. Okay, so I would just say mgh is equal to 1/2 kx squared, noting that we know what the k is and we know what the m is and we know what the height is, and gravity is a constant on planet Earth. We use 10 in my class, but you can use whatever you want. You just do this, the compression of the spring would be 2 mghs over k square rooted, and that would tell me x of it. But you can also solve it a different way. We could compare the location B to location C, but we would also know that the location B, it has the same amount of energy that it does at A, and the amount of energy it has at A is equal to mgh. To figure out how fast it's going at location B, we would just say that we would choose the two ideas of A and B, and we'd say mgh equals 1/2 mv squared. So one of the problems I see students having with these introductory classes is they don't know when to choose which to look at. They see 3 statements of equal, and they think that you have to use all 3 all the time, or 4 or 5 statements that you may have written out. What you have to do is you just have to identify the one you're looking for and equal it to, or set it equal to, the one you know the most about. In this case, we knew the most about location A, so keep that in mind. The mass has been reduced. You see 2GH equals V, so I square root that. And then we see that V equals the square root of 2GH, a very similar statement that we have over here. And now you've got most of what you could be asked for. You could also be asked for the velocity at any location here, but as a result, you would need to know what height it is at any of these locations, because that's a new variable that we would need to know to solve for it. Algebra teaches us that if we only have 2 statements, we can only have, if we have one equal statement, then we can only have one unknown. If you have 2 unknowns, you have to set up a system of equations. Excuse me. All right, what do we got next? Let's look at a pendulum. Because pendulum is referenced in the Unit 3 objectives, I think that you should be aware of a pendulum, but not necessarily the period of a pendulum, but you should be aware of the energy transfers in it. So we talked a little bit about a pendulum. I talked a little bit about it in office hours this week, but you want to be aware that it oscillates from one location to another location to another location. But you can also pick any location in the middle. So we'll just call this A, and then we'll call this B, and we'll call this C. And then you can have that weird odd one that says, you could be asked for something right here. So we'll set all the way up on that one to figure out how we could do that. So this is the root of our problem. We'd need to know one thing. We would need to know the height, either the height relative from A to B. So how much distance did it fall attached to this spring? You would either need to know this information, which we could call H. We'll define what that H is here shortly. Sorry, that's not perfectly parallel to the base. Or we would need to know the velocity right here. We would need to know one of those 2 statements for any conservation of energy for us to work. Otherwise, we just have to set up relationships. But here we could figure out a lot of different things if we knew that. We can use the idea we can use something, trigonometry, to help us find what H is if we knew what this theta was. So I'm going to quickly go through a statement to help us understand what this H is related to that theta. And then we're going to set up an equilibrium and conservation of energy statement to relate A to B to D. We're going to talk about this as D. Okay. C is just the other end of the swing. It would just go like this, assuming frictionless. Okay, so there you have that in your mind palace. I'm going to show you how to get I'm going to show you how to get the height from the angle and relate those 2 back and forth. And then we're going to figure out the height and we'll find the theta given the velocity at location D. So I draw this diagram slightly larger and only including A and B. I draw a nice line across the side there, a dashed line here, and these 2 lines right here are parallel to one another. But this value right here would be the H. How high is it above? A couple things that you would want to be aware of, or the one thing that you would want to be aware of, is the length of this string. That length of the string has not changed. I know this isn't perfectly drawn, my apologies, but that length of that string is equivalent to the length of the same string later in its motion. You would see right now a right triangle, and I'm going to focus right now on this right triangle that I've highlighted in blue here. Now it looks like a sailboat. And we see this theta right here. We could define this length right here. It's irrelevant length, but we could find that length, and we would say that length is related to the hypotenuse and the angle, and we would say that is L sine theta, which is worthless information, unfortunately, but we could still find it neat. I paid attention in pre-cal. We could also find this one, which actually is valuable to us, and I find that the blue length right here would be L cosine theta. Note that L cosine theta is not quite as long as the entire length of the string. It's this short. Fortunately, that value is important to us to find the height. Why is it important to know the height? Potential energy, mgh. So what we can do to find h is we can set h equal to the statement L minus L cosine theta. And that gives us the information that we're looking for, relating the length of the string and theta to the height that it would achieve. Sometimes you might see people pull the L out and they would just write L times the quantity of 1 minus cosine theta. The more math I do to a problem, the more likely I am to make a mistake. So when I get to a correct answer, I stop. That's correct enough. That's what equals means. All right. So now we're going to say, now that we know the height, we can set the energy potential at location A from the earlier diagram equal to the kinetic energy at location B equal to that location D that we described. At location D, it's not all the way in the air. It's not as high as it will get, which means it still has some kinetic energy. So I'll just say UG D plus K D. Not to be confused with Kevin Durant, the one that has the coronavirus. So mg, in this case, now we know L minus L cosine theta. I almost wrote it in cursive, sorry. That will equal 1/2 mv squared. And that equals, I'm going to run out of space. Oh well. mg L minus L cosine phi, some new angle, plus 1/2 mv at location D squared. Note that if we know all of this statement, we can set it equal to this statement. The only thing we don't know here as of that's not here is the velocity. Note that the mass of the object is in every term, so we can eliminate it from every term. And then we can solve for that angle or solve for that velocity given one or the other. If we had to, you can do that. And then once you do that, I would do that. Note that you can't cancel out L because you have this plus statement. Algebra 1 tells me I'm not allowed to do that, and Algebra 1 was correct. So that's heights, angles, taken care of. And I'm going to give you a problem with a graph to look at to solve, to try out that other idea before we talk about it. Okay. Last thing we're talking about here is power. You really just need to be aware that power is the rate at which work is done or rate at which energy changes. There's that ugly statement with horsepower that we dealt with on our quest that we kept dealing with, 746, something silly like that, depending on who you talk to. So the College Board's not going to ask you to do that, so keep that in mind. But we just need to be talking about it as a rate. The most common question you have there is someone lifting up a weightlifter. So we got the human. There's an object here, and the object is here. So we have location A, location B, and it tells us it took some amount of time t to do that. So to solve this problem, we need to know how much energy did it start with. Here it is at the ground, 0 potential energy. I'm not worried about the internal energy. Yes, I know that if you burned the box, it would burn and release heat energy, but that's not what the energy we're changing here. The stick figure is just lifting up the object. So we would just take the change in UG. That's the amount of work done, or the change in energy in this case. And we divide it by the amount of time. Couple things that you would want to be aware of algebraically, if we want to talk about it as power is force times distance over time. We then see another statement that we could write from this. Distance divided by time. This is a constant acceleration problem. If it's a non-constant acceleration, we have a different issue. It's just force times velocity, because distance over time is a velocity. This is pushing an object at a constant velocity along the ground. Could be it, where you're just overcoming the force of friction with no acceleration. If you have acceleration, you have yourself a changing velocity, which means you need to take into account the change in kinetic energy at that point. But power is usually the tack-on question at the end. It isn't the crux of the issue. You need to know how much energy it began with and how much energy it ended with. Speaking of endings, I think that's where I'm going to call it today. I'm sorry that it was a little dry. There wasn't a lot of energy in the energy discussion. I will shortly post some questions on the Google Classroom, and I will be happily answering questions from 12 to 2 every day if you just click the link in the Google Classroom. I hope all of you have a wonderful day, and again, I cannot wait to watch you walk across the stage. I'm hoping that I can wish you well on your AP exam on May 11th at the school. If not, I will wish you well in that morning, and we can just sit and calm down right before we take it. If you have any more questions, I know this meeting isn't the most discussion-based. It's more information-based. If you have questions, please throw up noon today. The link is in Google Classroom, or tomorrow, or Wednesday, Thursday. I don't know about Friday. It's a bank holiday, but what does that mean right now? Anyway, have a wonderful day. I hope to see you soon. Bye.